What if the most dangerous part of going to Mars is not getting there, but trying to come home? Imagine surviving 6 or 7 months in deep space, landing on another world, walking beneath a salmon-colored sky, and becoming one of the first human beings to leave footprints on Mars. Then, after all of that, you discover the cruelest fact of the journey. Earth is millions of miles away. Your body has been weakened by space. Your spacecraft has only one chance to launch, and if anything fails, no rescue mission can reach you in time. Mars has often been presented as humanity's next great destination, a place where explorers might build habitats, search for evidence of ancient life, and eventually establish a permanent human presence. But nearly every beautiful image of astronauts standing on the Martian surface hides a much darker engineering problem. Going to Mars is difficult. Returning from Mars may be even harder. To understand why, begin with the distance. Mars is not parked at one fixed point beside Earth. Both planets orbit the Sun at different speeds, and the distance between them constantly changes. At favorable moments, Earth and Mars can be tens of millions of miles apart. At other times, they are separated by hundreds of millions. That means a Mars mission cannot simply leave whenever it wants and return whenever the astronauts feel ready. Orbital mechanics decides the schedule. A spacecraft traveling between planets is not moving across a static map. It is entering a vast gravitational choreography involving Earth, Mars, and the Sun. Mission planners usually take advantage of launch windows that occur roughly every 26 months, when the planets are positioned favorably for an energy-efficient transfer. Miss the right geometry, and the journey becomes much harder. For astronauts standing on Mars, that creates a disturbing reality. They may arrive knowing that Earth is effectively unavailable for many months. The return trip has already been shaped by planetary motion long before they stepped onto the Martian soil. There is no emergency flight home, no helicopter, no rescue aircraft, no nearby station. If a serious problem develops, the astronauts may be living inside a world where survival depends on equipment that must continue functioning until the planets themselves allow the journey home. And even when the return window arrives, Mars still refuses to let them go easily. Mars has gravity about 38% as strong as Earth's. That is weak enough to make launching from the surface easier than launching from Earth. But it is still powerful enough to require a real rocket. That rocket must somehow be waiting on Mars. It must survive months or possibly years of extreme cold, dust, radiation, and mechanical inactivity. Its fuel must remain usable. Its guidance systems must function. Its engines must ignite correctly. And unlike a rocket launching from Earth, there may be no army of technicians standing nearby. On Earth, launch vehicles are inspected by enormous teams. Sensors are tested, components are replaced. Engineers monitor thousands of parameters. If something looks wrong, the launch can be delayed. On Mars, a small crew may be both the astronauts and the repair team. Then comes ignition. For the people inside the vehicle, everything they have survived up to that point becomes almost irrelevant. A failed valve, damaged sensor, clogged fuel line, software problem, or engine malfunction could trap them permanently on the planet. The margin for error becomes frighteningly small. NASA and other space agencies have studied many architectures for sending humans to Mars, and the return problem appears in almost every serious design. One concept is to send the return vehicle ahead of the crew. Another is to manufacture some of the required propellant on Mars itself. That idea is known as in situ resource utilization. Mars has an atmosphere dominated by carbon dioxide. In principle, technology could use Martian resources to help produce oxygen and possibly fuel components rather than carrying everything from Earth. The attraction is obvious. Rocket propellant is heavy. Carrying the fuel required to leave Mars all the way from Earth increases the mass that must first be launched from Earth, which then demands more fuel, which itself adds more mass. This is the tyranny of the rocket equation. Every kilogram matters. The problem is that making fuel on Mars transforms the planet into part of the spacecraft. Now the return mission depends not only on the rocket, but also on a chemical factory operating on another world. NASA's Perseverance rover carried an experiment called MOXIE that successfully produced oxygen from carbon dioxide in the Martian atmosphere. It was a remarkable demonstration that a basic form of resource utilization can work on Mars. But producing small experimental quantities of oxygen is very different from creating, storing, verifying, and protecting the large amount of propellant infrastructure needed for a crewed launch. A human return vehicle would need extraordinary reliability. The factory cannot simply work most of the time. It must work when human lives depend on it. That is one of the recurring patterns of Mars exploration. Technologies that seem manageable in a laboratory become far more intimidating when failure means there is no second chance. Leonard Susskind is not a Mars mission engineer. His career is focused on some of the deepest questions in theoretical physics, quantum mechanics, string theory, black holes, information, and the nature of space-time. But the worldview that emerges from fundamental physics offers an important reminder about Mars. Nature does not negotiate. The universe does not care about human ambition. The equations governing energy, momentum, gravity, and radiation remain exactly as unforgiving, whether the traveler is a machine or the most famous astronaut in history. Mars is not dangerous because it is hostile in a conscious sense. It is dangerous because the laws of physics are indifferent. That indifference becomes especially clear when we consider what happens to the human body. A crew traveling to Mars may spend many months in microgravity before landing. During long periods without normal gravity, muscles weaken and bones lose mineral density. The cardiovascular system adapts. Balance can be disrupted. The body begins reshaping itself for an environment it was never designed to inhabit. Astronauts aboard the International Space Station exercise for hours to reduce these effects, but exercise does not completely erase them. Mars offers partial gravity, not Earth gravity. We still do not have direct long-term human data showing exactly how years of Martian gravity would affect the body. That is one of the largest biological uncertainties of permanent human settlement. Would 38% of Earth's gravity be enough to maintain healthy bones, muscles, cardiovascular function, and development over long periods? We do not yet know. And eventually, returning astronauts would face the opposite transition. After months or years in reduced gravity, they would leave Mars, enter microgravity again, spend months traveling through space, and finally return to a planet where gravity is more than twice as strong as what they experienced on Mars. Earth, the place they once thought of as home, could suddenly feel physically oppressive. Imagine lying down while someone gradually adds weight to every part of your body. Your heart must pump harder. Your muscles must support more load. Standing becomes work. Astronauts returning from the International Space Station often require medical support as their bodies readjust to Earth's gravity after months in orbit. A Mars crew could be returning after a far longer and more complex exposure. And gravity is only one part of the problem. Outside the protective environment of Earth's magnetic field, astronauts are exposed to a harsher radiation environment. Galactic cosmic rays are high-energy particles arriving from outside the solar system. Solar particle events can produce sudden bursts of energetic radiation from the sun. On Earth, the atmosphere and magnetic field provide enormous protection. Deep space provides much less. Spacecraft shielding can reduce exposure, but shielding against high-energy cosmic radiation is difficult. Some particles can penetrate material and create secondary radiation when they collide with the spacecraft structure. A Mars mission involves radiation exposure during the outbound flight, time spent on Mars, and then another long exposure during the trip home. The return journey does not reset the radiation dose, it adds to it. Mission planners therefore face a problem that cannot be solved simply by building a faster computer or carrying more food. Radiation is a fundamental environmental hazard of deep space. A severe solar particle event during the journey could require astronauts to shelter in a better protected region of the spacecraft, perhaps surrounded by water, food supplies, or other mass that can help absorb radiation. But cosmic rays are harder to stop. The long-term consequences involve increased risks that scientists continue to study, including cancer and possible effects on the central nervous system and other tissues. Now imagine that all of this is happening inside a spacecraft that may be smaller than an average apartment. The crew has already spent months together traveling outward. They have lived on Mars in an isolated habitat. Then they must spend months together again coming home. There is no walking outside for fresh air, no private drive, no weekend away from the team. Communication with Earth is delayed because radio signals travel at the speed of light and Mars can be many light minutes away. A message sent to mission control may take minutes to arrive, and the response takes minutes to return. A real-time conversation is impossible. For the first time in human exploration, a crew traveling on another planet may need to handle major emergencies without immediate instructions from Earth. That independence is often described as a strength, but psychologically, it has another meaning. They are truly alone. The astronauts know that if a medical emergency occurs, the nearest advanced hospital is another planet. There is another hidden problem waiting inside the return spacecraft: mass. Every liter of water, every meal, every replacement component, every medication, every radiation shield, and every life support system adds weight. On Earth, we take infrastructure for granted because it surrounds us. On a Mars mission, infrastructure must travel with the crew. Air must be managed. Carbon dioxide must be removed. Water must be recycled. Waste must be handled. Temperature must be controlled. Electrical power must remain available. Critical systems may need backups, and the backups themselves add mass. This creates one of the cruel paradoxes of spacecraft design. The more safety equipment you add, the heavier the vehicle becomes. The heavier it becomes, the harder and more expensive it is to move. You want redundancy because failure is deadly. But redundancy comes with a physical cost. Then Mars adds dust. Martian dust is fine, pervasive, and potentially damaging. It can settle on equipment and solar panels. It may enter mechanical systems. It can cling to spacesuits and potentially be brought into habitats. Mars is famous for dust storms, including planet-encircling events that can dramatically reduce sunlight. A return vehicle left on the surface for months must survive that environment. If it relies significantly on solar power, prolonged dust conditions become a serious design concern. Nuclear power may reduce dependence on sunlight, but it introduces its own engineering constraints. The brutal truth is that a successful return from Mars is not one problem. It is hundreds of problems linked together. And the most frightening failures may occur before the return rocket even leaves the ground. Suppose the crew produces enough fuel. Suppose the ascent vehicle launches successfully. Now they must rendezvous with another spacecraft in Mars orbit, depending on mission design. Orbital rendezvous is a mature capability near Earth. Humans have performed it many times. But around Mars, the situation changes. There is no rescue spacecraft nearby, no second crew waiting at another station. If the ascent vehicle enters the wrong orbit, the crew may have limited fuel to correct it. If docking hardware fails, two spacecraft carrying everything required for survival could drift within sight of each other and still be unable to connect. Then, once the crew begins the journey home, the sun takes control again. The spacecraft must follow a path that intersects Earth months later. Navigation must be extraordinarily precise. Small errors can grow over enormous distances, although spacecraft can perform trajectory correction maneuvers along the way. Engines, thrusters, star trackers, computers, antennas, and power systems must continue functioning for a mission that has already lasted perhaps years. We sometimes imagine spacecraft as machines that either work or fail. Reality is more subtle. Components degrade, sensors drift, materials experience thermal cycles, radiation can affect electronics, seals age, filters accumulate contaminants, mechanical systems endure vibration, temperature changes, and repeated use. Reliability becomes a battle against time. And then, after millions of miles, Earth finally grows from a bright point into a world. That should be the easy part. It isn't. A spacecraft returning from interplanetary space approaches Earth at high speed. To land, it must lose an enormous amount of kinetic energy. Earth's atmosphere becomes both the solution and the danger. Atmospheric entry converts much of the spacecraft's kinetic energy into heat through compression and interactions with the atmosphere. Heat shields protect the vehicle from extreme temperatures. Humanity has done this before. Apollo astronauts returned from the moon at tremendous speeds. Robotic sample return missions have also entered Earth's atmosphere after interplanetary travel. So Earth return is not an unknown physical concept, but a crew coming from Mars would be completing a mission of unprecedented duration and complexity. The heat shield may have spent years in space before being asked to perform perfectly for several terrifying minutes. There may be no practical way to repair its most critical hidden structure immediately before entry. The crew could travel hundreds of millions of miles and still be lost during the final fraction of the journey. That is one reason Mars mission engineering feels almost cruel. Success must be continuous. You do not receive partial credit for reaching Mars. You do not receive partial credit for launching from Mars. You do not receive partial credit for reaching Earth. Every major link in the chain must work. History has shown how difficult Mars already is for robots. Since the beginning of the space age, numerous robotic Mars missions have failed because of launch problems, communication failures, navigation mistakes, software errors, hardware failures, and entry, descent, or landing accidents. Some spacecraft vanished. Some crashed. Some lost contact. Others became extraordinary successes. Those successes have taught us how to orbit Mars, land robotic spacecraft, operate rovers, fly a small helicopter, study the atmosphere, drill rocks, and analyze the planet with remarkable precision. But humans change the equation. A robotic mission can fail tragically from a scientific and financial perspective. A crewed mission carries people whose survival must dominate every decision. That is why one-way fantasies about Mars sometimes appear in popular culture. If returning is so difficult, why return at all? The answer is that permanently abandoning a crew is not a technical solution. It simply transfers the difficulty into an even larger challenge, keeping humans alive indefinitely on a planet with no breathable atmosphere, low pressure, intense cold, radiation exposure, limited accessible resources, and no existing industrial infrastructure. Mars is not a second Earth waiting for settlers. At present, it is a world where human life would depend on machines every hour of every day. Take away pressure, and the environment becomes lethal. Take away oxygen, and the environment becomes lethal. Lose heat during extreme conditions, and survival becomes difficult. Lose water recycling or critical power systems, and the clock begins ticking. A permanent settlement would eventually need deep redundancy and the ability to manufacture replacement parts, maintain habitats, produce food, manage medicine, and perhaps expand without constant dependence on Earth. That may one day be possible. It is not the same as placing a flag on the surface. This difference between reaching a place and truly living there is where the romantic story of Mars collides with physics. Susskind has spent decades thinking about boundaries, black hole horizons, causal limits, the information accessible to observers, and the strange ways physics changes when we confront regions we cannot freely communicate with. Mars is not a black hole, of course, and the analogy should not be taken literally. But for a human crew, distance creates its own kind of operational horizon. Earth remains visible in principle, reachable in principle, and emotionally central. Yet it is too far away to provide immediate help. That gap changes everything. For most of human history, exploration still allowed some possibility of return through familiar environments. Ships crossing oceans could carry provisions, repair timber, collect rainwater, fish, or encounter land. Mars offers no breathable coast. There are no forests for emergency shelter, no river you can safely drink from, no ecosystem waiting to absorb your mistakes. Every basic human need has to be mediated through technology. The first people to return successfully from Mars may therefore experience something no humans have ever experienced before. They will watch Earth grow larger through a window and realize that the blue planet is not just home. It is the most sophisticated life support system humanity has ever known. Its atmosphere repairs itself through vast natural cycles. Its magnetic field helps shield the surface. Its ecosystems recycle matter. Its oceans regulate climate. Its gravity shape the human body. Everything we call normal is the result of living inside an extraordinarily complex planetary environment. Mars reveals that by removing nearly all of it. Perhaps this is the deepest lesson of the return journey. We often talk about becoming a multiplanetary species as though planets were simply destinations on a map. But the space between worlds is not empty in the practical sense. It is filled with radiation, orbital constraints, energy requirements, biological consequences, communication delays, and probabilities of failure. Physics makes every mile matter. Engineering makes every kilogram matter. Biology makes every month matter. And psychology makes every human decision matter. None of this means humans cannot go to Mars. There is no established law of physics that forbids a round-trip crewed mission. The challenge is not impossibility. The challenge is that nature demands payment for every step in energy, mass, complexity, time, and risk. One day, astronauts may launch from Mars and begin the long fall through the sun's gravity toward a meeting point with Earth. Behind them, the red planet will shrink. Ahead of them, home may still be too distant to distinguish as anything more than a bright speck. For months, they will exist between worlds, belonging fully to neither. And perhaps during that journey, one of them will look through a window at the darkness and understand something that photographs can never communicate. Human beings were born inside a thin layer of atmosphere wrapped around one small planet. Every civilization, every war, every love story, every city, every language, every person who ever looked at Mars and wondered whether we could reach it existed within that narrow shelter. Going to Mars may prove that we can leave it. Returning from Mars may teach us what it actually means to have a home. And when the first Mars travelers finally see Earth filling their window again, the most haunting question may not be whether humanity can survive on another planet. It may be why, after discovering how brutally difficult it is to live anywhere else, we ever imagined our own world was ordinary.